presentation. After me will be Shruti, will be presenting to you all engine analysis, so you get to see all the numbers that we have come up with. First of all, I'll go through what we went through last week. I'll show you all what are the deliverables that we have from last week, and then I'll go through how we're splitting the work. Next, I'll talk about the independent flight and underwater phase system, followed by a possible integrated propulsion system, which is of course of interest. Last week we selected a turboprop and a diesel/petrol electric engine to power different phases of the SFV mission. And also we selected an impeller-driven pump jet, which is a pump jet that is fitted inside of this holes. These are the action items from last week. We talked about the ability to survive after being immersed in water for the turboprop, and we also discussed about thermal shock of the engine. For the integration of the systems, I mentioned that we wanted to operate the turboprop underwater and what are the possible problems that we have, and also the recharging of batteries using the turboprop. This is the work allocation currently that we have after last week, that we decided to split the job in such a way. I'm covering mainly the integration of the system. Shruti is covering mainly the turboprop, and together we are trying to work a way to use the air propellers as marine propellers as well. Right now, Chris is working on the layout of batteries, the motor, the reduction gearing, and the design of the marine propeller. Based on this values given to me by Chris, he wanted 80 kWh of batteries in total to power the submarine in the underwater phase. So of course we need to charge the batteries, so I took a look at some of the generator. What we wanted is to charge the battery during the loiter phase. So our aim is to actually charge the battery within 24 hours. This would mean we need 3.34 kilowatt of power per kilowatt per hour to charge the battery within 24 hours. We also want a generator that is not too noisy, because of course this will make the ride to the loiter phase pretty uncomfortable for the pilot, because we'll be using the generator. Here are some examples that you can see of the noise levels. And we want something with automatic voltage regulation. Typically aircraft operates on a 400 Hz AC power with a 115 voltage. So that's something that the system people should look out for when deciding on electrical systems, because this is what power is normally. We also want something that's light, compact, and electric start capable, of course. Here are three different diesel/petrol engines that I've looked into. Diesel engines are generally more fuel efficient, but they are larger because we'll need greater noise reduction, because petrol generally burns quicker. Currently I'm looking at based on these values, such as the weight, including the additional fuel that's required to charge the batteries, the time required to charge the batteries fully, and of course the total volume after accounting for efficiency of charging batteries. The Pramac S8000E seems to be the ideal one. Here's a look at it. It's not too heavy, probably about 100 kg. Since we have diesel/petrol electric engine, of course we need a snorkel that provides air to actually for combustion. So for a snorkel, you need a snorkel for ventilation purposes, and of course I mentioned earlier, provision of air for the engine. When you charge batteries, you are actually producing hydrogen gas. So it's, of course, since you're producing hydrogen gas, it's not very safe to have it above a certain concentration in the air. So that's why we need a snorkel to actually vent all this gas out, and also exhaust. For the design of a snorkel, I took a look at some papers and realized that it is generally to prevent structural damage. We have it 30 feet from the keel, and you can only travel 7 knots at this with a snorkel. For the sizing of a snorkel, I intend to use a control volume analysis, but just for comparison, a family car produces 100 horsepower, which is around 74 kilowatts, and our generator produces 7.5 kilowatt of output. So that would mean like a snorkel like this, we probably need something that is smaller. And we have for snorkel, one concern that my crewmates asked me is about how do we prevent water from entering the snorkel. We generally have a float valve over here to prevent water from entering the snorkel. When water gets in touch into the mask, we have an electrode. It actually breaks and gets in contact with the electrode. It actually breaks a simple electric circuit, and this float valve will close automatically. With a snorkel, of course, you need an exhaust. So this is generally the look of the exhaust system. I mentioned earlier that you need to remove H2, and these are the explosive limits. Again, I intend to use control volume analysis, which won't take me so long, but it's not yet ready. We have a hull valve to actually ensure that the exhaust gas passes through the pressure hull, and of course we have muffler to reduce noise through acoustic soundproofing. Just an interesting fact is that normally, like huge submarines, we have the muffler tank is capable of being flubbed to actually allow the submarine to dive. But in this case, I would not expect the muffler to be too big to actually carry a lot of water to allow the submarine to dive further, dive easily. We also talk about the survivability in seawater, which is water damage. We need to prevent water from seeping into the engine. That's why we intend to pack the engine into the fuselage, but I'm not too sure if I mentioned to Gerald yesterday, so this might be a possibility and some changes might be made. For boats, we generally have a stuffing box to prevent corrosion of the shaft. I will talk more about this, the operation of the stuffing box later. And of course, we want corrosion-resistant material for parts exposed to the seawater, such as the air propellers when we are in the submerged phase. I intend to use aluminium bronze or perhaps carbon fiber. This is something new that are corrosion-resistant to seawater. This is the operation of a stuffing box. We have a gland seal which actually compresses the packing ring and lantern ring so that water does not enter the shaft. And the lantern ring is actually there to provide some form of lubrication to the shaft, as well as to help cool the shaft and allow for heat dissipation. We also have a valve and flow meter that accurately control the amount of lubricant that is flowing into to lubricate the shaft. This is generally 40 to 60 drops per minute. For thermal shock, I'd just like to remind you what it is. It's the material being prone to damage with sudden change in temperature. This is especially important since we intend to submerge the aircraft after operating the engine in flight. This problem will be solved if we actually pack the engine into the aircraft's fuselage, and also the exposed shaft can be cooled by using the stuffing box. If in any case that the engine has to be exposed, we can actually, this will be quite a bit of challenge for the pilot because for time saving, we can actually switch off the engine before landing and employ high lift devices to allow a smooth landing. But this will depend on the skill of our pilot. I look at some forums. Technicians generally they wait for 30 minutes before actually working on the engine, meaning that they have to actually touch the engine. That's why I got the time of approximately 30 minutes to actually cool the engine before submerging it. Here is a look at the integrated system that we have for now. I intend to have the two systems to actually be sharing batteries. This is level 1 of integration. I will talk about the next level. That will be using the air propellers as marine propellers as well, which can be a huge challenge. In an integrated drive generator over here, we usually have first of all, we have an alternator that rotates at a specific revolution per minute. And of course, we will want to supply power at this frequency and voltage that most electrical appliances in the aircraft uses. Then we have a constant speed drive, which allows for varying input that is from the compressor, and the output will stay constant. With the alternator and the constant speed drive, we will call it an integrated drive generator. To charge the batteries, currently I know that it's going to be 4.2 volt battery, so you need a transformer to actually change the voltage from 115 volt to 4.2. This is a higher level of integrated system that we want. We want you can see now that the marine propeller is being removed with the air propeller still being here, and then we will share propellers for both underwater and flight phase.
Sorry, can you go back just a second?
Okay, for operating of air propellers as marine propellers, it will take some time to actually come up with a proper analysis since we just finished the turboprop engine analysis, so I will expect it to be delivered maybe in 1 to 2 weeks time. We will need, for air propellers, generally we have optimal tip-speed ratio, which is the ratio of V-tip to the free stream velocity, with V-tip given as R omega. In general, we want the propeller to have a high RPM, so long as the tip speed ratio the tip speed doesn't reach the speed of sound, because we do not want the formation of any shock waves. So that's a limiting factor in this design. I believe that many people here just now mentioned about cavitation, and of course, if we intend to use air propellers as marine propellers, there will be some form of cavitation-induced erosion. I'd like to remind you all that cavitation occurs because of rapid changes in pressure that results in voids, also known as bubbles. It occurs when the local static pressure is less than the vapor pressure. Vapor pressure is the pressure induced by vapors in thermodynamic equilibrium. So the problem of cavitation is not the evaporation of bubbles, but more of the collapsing of bubbles, which will induce increase in pressure and quite possibly a shock wave, hopefully not too strong. And we have these two forms of cavitation, which is one of which is inertial cavitation, and the other is a non-inertial cavitation, which usually has some form of oscillation. One example that we use non-inertial cavitation in ultrasonic cleaning, which is employed in cleaning jewelries and stuff like this. There are a few possible solutions to this, which is a super cavitating propellers. Basically, we have a wedge shape that forces cavitation to occur at the leading edge, and with this, the bubbles will actually not be causing any erosion of the propeller blades. The other thing is to have the blade to rotate slower in water. With an increase in local static pressure, we are unlikely to have the local pressure to be less than the vapor pressure, so cavitation will not occur. And that's it for my part. Questions?
At the beginning of your presentation, you were mentioning diesel and petrol propellers.
Yep. No, diesel and petrol generators.
Yeah, sorry. It's been a holiday.
Agreed.
What about fuel? So, what fuel are you planning to use for your turboprop?
That, of course, should be jet fuel.
So you're using Jet A1 for your turboprop, and so you'll have to carry a second type of fuel for.
Yeah, exactly. But if we have an integrated system like this, then we will automatically charge the batteries using IDG.
Okay.
So currently we are trying to look into this after this presentation.
The integrated drive generator on this one, I expect, is the diamond shape rather than the box.
Oh, okay. It's
Yeah.
just a understand.
Because it's also
Yeah.
a road. About the snorkel length, you basically said that there's a maximum height of 10 meters, roughly.
Yeah.
Do you guys intend to use to recharge the batteries while submerged, or is that only while?
If you are intending on using the turbo prop to recharge, if I'm not wrong, to avoid sea state 5, we intend to have the wing just floating above the water level. So in that case, we will not need to have a snorkel because we can use a retractable inlet that goes through to our aircraft and provide air.
You said, sorry.
Yes, okay.
You said you need a 80 kilowatt battery.
Yeah.
Where does it come from?
Based on last week, we made a calculation. Chris made an estimation on this. So basically, it's one ton of batteries approximately. And this 80 kilowatt, I think, is based on individual submarines of 6 to 8 people, right?
Yeah.
Yeah, and we also accounted for a factor of 1.5 and some form of redundancy.
Okay, but it would be nice to see at the end the proper calculation of the energy you need and the efficiency of the whole system that you want to implement needs to be taken into account as well. And another thing, why a battery and not a supercapacitor? Just throwing it there.
We haven't actually looked into supercapacitor.
Yes, they would be faster to recharge and they wouldn't have the hydrogen production.
But there's still quite a new technology, and we need technologies within 4 years. And also they give relatively low current.
Low current.